So, in the last chapter, chapter 15, we looked at differentiation when you have functions of several variables. Chapter 16, we're going to talk about how we integrate these functions. Just like with derivatives, we kind of looked at them one derivative at a time. That's kind of how integrals work. But just to kind of remind you of the story of the integral, we started off, we had a continuous function over some closed bounded interval AB. And we were trying to figure out what the area was. And so what we did is we went in and chopped the interval up into equal pieces. And then we sampled the function at values in each of these little subintervals. Okay. And then what we did is we took the function value times the length of the subinterval, and we could interpret that as an area of a rectangle. All right. So once again, the big idea is we chopped up the domain into pieces. We sampled the function at points within each of those little pieces, and then we added them up. And in this case, we're adding up the volume of, or the area rather, of rectangles, which approximated the area under that curve. And you could pick any point you wanted to, as long as your function was continuous and you took a limit that made sure the rectangles got skinnier and skinnier. Then no matter how you decided to pick these points in the subintervals, you would get the same limit at the end, as long as your function was continuous. And then we had the fundamental theorem of calculus, which said that you could sort of circumvent the limit process as long as your function was continuous on the closed bounded interval AB. Then you could calculate this quantity by looking at the difference in the antiderivative at any antiderivative from B to A. Okay. So if we look one dimension up, the analogous problem in Calc 3, instead of looking at a function y equals f of x, we'll look at a function z equals f of xy. And instead of looking at the area between the graph of that function, which is a curve, and the x-axis, we could look at trying to figure out the volume between that surface and the xy plane over a closed bounded region. Okay? So for the first day or so, we're going to assume that the region down here is a rectangle. And then we'll generalize here towards in the next, Wednesday or so. We'll generalize to other regions. All right. So we can come in and do the same kind of thing. We can chop up the x-axis into some equal pieces. But we can also chop up the y-axis. Because x and y are considered independent variables, we can also chop up the y-axis. And what that's going to do is produce for us a little grid down here in the xy plane. And what we can do is we can go in to each of these squares or rectangles, and we can sample the function at each of these points. And we can go about trying to calculate a volume of one of these rectangular prisms. Right? So the height would be like your f of xy, that would be the height. And then what we would have down here, that would be your area, that would be your delta x times delta y. And if I take height times the base, that's going to give you the volume. We get something like that. And because continuity works the same way it did in Calc 1 or AP Calculus, it's not going to matter which points you pick as long as you guarantee that those little squares get smaller and smaller and smaller. So one way they can kind of force that to happen is they'll force the diagonals of these rectangles to go to 0. So if the diagonals of the rectangles all go to 0, that's going to shrink those rectangles down to individual points. So no matter where you've picked a point in the rectangle, they'll all go to the same place. So once again, something you should do in the privacy of your own home is to take a look at this picture here and what's happening and compare that to the kind of stuff you did back before. And hopefully you realize this is just one dimension up. We just have an additional independent variable that gives us an additional dimension on the domain. And you're going through, but we're doing the same thing. So now we would have a double sum. We'd be adding up over the x-axis and the y-axis. So if we chop the x-axis up into m pieces and the y-axis up into n pieces, we'd have m times n squares to deal with. And so we would fix an m, and then we'd add up what's going on, all the y's. And then we would do that for all the x's. And then that's one way to go through and add up all of those squares, sort of going one row at a time. And so as usual, to get a better and better approximation, we would use a finer and finer grid. And this limit then is what we would call the double integral over r, f of x, y, dA. So the two integrals here are indicating the fact that we've got two independent variables, x and y. And the dA is called the area differential, which it's going to take on a couple different formulas for us. For right now, we can either think of that as a dx dy or a dy dx, depending on how you want to chop things up first. But that area differential represents an infinitely small square, or rectangle. I guess it doesn't matter. So this represents a little infinitely small patch of area. You can think of the function as representing an infinite a height at a specific point. So a height times an area, you can think of that as a volume. And what these double integrals are doing is we're adding these up in both directions. Right? So we're getting a sweeping motion that just adds up all of these infinitesimal volumes to give us the volume of a certain region in space. So I always like to go through one of these. If you had me for Calc 1, you know that we went through the whole Riemann sum process, taking limits on those and using formulas and things like that. I'll assume you've already had all that stuff at some point, but I do want to do one example where we actually go through and do an approximation, because this is how double integrals will often get used out in the wild. Okay, so we've got a little grid set up here. The values of the function f over the rectangle 0, 1 by 1, 4 are summarized below. I'm going to mute you there, Rick. Approximate the double integral using a Riemann sum with m equals 2 and n equals 3. So we'll chop the x-axis up into 2 equal parts and the y-axis up into 3 equal parts. That'll give us 6 little rectangles to work with, and we're supposed to sample the function using the values in the upper right corner. So let's see if we can actually sketch this out. So x is going from 0 to 1. Y is going from 1 to 4. I'm going to chop the x up into 2 equal pieces. So that's going to give me 0.5 and 1. I'll chop the y up into 3 equal pieces. I'm going to give myself some more room. So 3 equal pieces. So here we go. So the rectangle we're chopping up would be this rectangle here. And we're chopping up the x. We've got 2 equal parts in the x and 3 equal parts in the y. And so those are our 6 squares. So if I look at my delta A sub I, or delta A in this case, it's all the same because the area of these little rectangles are all the same. They're all going to be how wide. So if I pick any one of these rectangles here, I'll just label them. Each rectangle is going to be how wide. Yeah, half. And they're each going to be how tall. 1. So each of these little rectangles are a half square unit. Okay? Now what we want to do is we want to go through and we're going to multiply this by the function value, and it says here at the upper right corners of those little sub squares. So I'm looking at these points here. So once again, each little sub-rectangle there, we're going to evaluate at a particular point. That's sort of the recipe we're using. We could use center points. We could use some other way. Just like in Calc 1, you could use midpoints, right endpoints, left endpoints, or whatever. But that's just the recipe they give us here. So if I look at the first square, the f of x, y we want, what would that be? So the x would be 0.5, the y would be 2. So if I go 0.5, comma 2, yeah, that's your negative 1.3. So if you look at f of 0.5, comma 2, you'd have negative 1.3 times 0.5. And that would give you what? And I can interpret that as a units cubed if I wanted to. Okay? So that would mean that this surface, instead of being above the xy plane, would be below the xy plane. Negative 0.65. Yeah, it's 13 divided by 2 is 12 and a half. Or 6 and a half. Okay? So that's how we would get the calculation for rectangle 1. All right, and then for rectangle 2, I'd look at the coordinates here. So x is now 1, y is still 2. So x is 1, y is 2. That's 5.3. So I take the 5.3 times the 0.5, and I would get that value. So the double integral over r of f of x, y dA would be just going through each of those values. So we'd have f at 0.5, comma 1 times r 0.5 plus f at 1, comma 1. Wait, I'm sorry. Was that 1 or 2? We were doing. It's at 2. Times 0.5 plus, then we go in here for square 3. The x would be 0.5, the y is 3. So f at 0.53 times 0.5 plus f of 0.5, excuse me, f at 1 comma 3. So for square 4, we're looking at 1 comma 3. Times 0.5. And then we're looking at this top row here. The fifth square, the x is 0.5, the y would be 4. We'll plug that in, multiply by the delta A. And then finally the last square, x is 1, y is 4, 0.5. I should put an approximation here. Okay. So in each case, we're sampling the function in those little rectangles. Think of that as a height, either above or below the plane. And then our dA, think of this as the area of the base. You can go through all those calculations, and you should get roughly 15. Okay. All right, so do you see how what we're doing here is just what we used to do, but one dimension up? We're chopping up the domain. In this case, the domain is a two-dimensional rectangle. Back in Calc 1, it was a one-dimensional interval. We're sampling the function at points in the domain, and then we're multiplying it there. Instead of multiplying by length in one dimensions, we're multiplying by area because it's two dimensions. So height times area gives volume, length times width gave area, so there it is. All right, because limits work the same way as they did before, we would be getting a limit of a number here. And the properties of sums are the same because it's the properties of arithmetic. We've got the properties of the double integral. First off, the double integral respects sum and differences, so you can either add or subtract and then find the integral, or find the integral of each thing and then add or subtract. Assuming, of course, f and g are continuous, so that you know that these integrals individually exist. You can factor constants out of summations, and you can factor constants out of limits. So therefore, you can factor constants out of integrals. It maintains the inequalities like the integrals did in Calc 1. If you've got one surface living below another surface, then the integral below the one surface will be less than or equal to the integral under the other surface. So if the things you're adding up are less than or equal to, then the sums are going to be less than or equal to. And let's take a look at this property, because this looks kind of weird. If R equals R1 union R2, where R1 and R2 are an overlap of no area, then you can add those integrals. We had something like this back in Calc 1, or in AP Calc. We had something, it was called the additive interval property. The additive interval property looked like this. Let's say you got yourself a function, continuous function over a closed bounded interval AB. And let's say you got C in there. Then the integral from A to B of f of x dx could be calculated by integrating from A to C f of x dx plus C to B f of x dx. In other words, you can kind of take a little break. And the reason that that's totally fine is because when I add up from here to here, and then I add up from here to here, the only overlap we've got would be that vertical line, which has no area. Okay. And this was the kind of thing you did, like if f weren't quite continuous, if you had like a little jump discontinuity, like let's say your function looked like this, and you had like a little jump here, that allowed you to actually integrate that without stressing out too much about what's happening here. So what's the analogous thing here in Calc 3 is you've got your region, say your region in the plane, that's your region R, and you're integrating over that. And once again, in section 16.1, we're just sticking to rectangles, but we'll quickly move into these other regions. Let's say you've got, this breaks up naturally into two parts. So you've got like an R1 and an R2. Then if you're trying to figure out the double integral over R, then you can just integrate over R1 and then integrate over R2. As long as their overlap has zero area, meaning that the corresponding volume then would be 0 too. So this is just the multi-dimensional version of the additive interval property. Yeah, you could do that. Yep. If you had something that was more than overlap, so like if you had, for whatever reason, if you had like this, and you called that R1, and you called that R2, and then you had some non-trivial overlap, so R1 intersect R2, yeah, you could totally do that. And we'll see this kind of stuff when we get into the vector calc here in chapter 17. But the integral over R, let's say R is R1 union R2, so R is the whole thing, that'd be the integral over R1 plus integral over R2. But if you did that, this would get counted twice. So we'd have to take off one of those integrals. Yeah, very good. All right, so as mentioned earlier, the way we avoided the limit process is we proved the fundamental theorem of calculus, which essentially, that was a courtesy of the mean value theorem. We could replace all of that discrete summations by looking at an antiderivative. So the way we're going to do it here is we're going to use that fundamental theorem of calculus, but one variable at a time. So back in the day, right, back in the last chapter, we would have partial derivatives. And when we took a partial derivative with respect to x, we treated y as a constant. So we could factor the 6 and the y out. We just get 6y squared. Well, now we can do the same thing. We can do partial integrals. If I wanted to integrate 6xy squared with respect to x, y is no longer tied to x. Y is no longer a function of x. So we'll just treat the 6 and the y as a constant. And so we'll do all kinds of things. We'll just move those out. And now we can integrate. But here's where we're going to have to be a little careful if we have indefinite integrals. I'm sorry, it should be dx, yeah. Because if I've integrated with respect to x, then that constant would be a constant as far as x is concerned. So if we do the indefinite integrals, and we have our arbitrary constants, they could actually be functions of y. And we'll see this a little later in the next chapter, but I want to point it out now. So if you're just looking for general antiderivatives, if you integrate with respect to x, your arbitrary constant, your c, could depend upon y, and vice versa. So let's take a look at this first example We're integrating from -1 to 2, 6xy squared dy. So the first thing is we're integrating with respect to y. So it's just like when we were taking derivatives with respect to y in chapter 15. We're going to treat the 6 and the x both as constants. So if I could factor those out of the integral. Then I can integrate this like I would back in Calc 1. You just find an antiderivative, substitute in y equals 1 to y equals 2. If you've had me throughout the calc sequence, when I do the evaluations, I always put the letters along with it. Thank you, -1. To make sure we know what letter we're subbing for, whether it's x or u. But now you need to know, is it x or y? You follow? So you always want to put those letters there when you do something like this. So you got your 6x, 8/3 minus 6x times a -1/3. So you add these together. You'd get 6x times 9/3, which would be 18x. So you've integrated out the y, and now you're left with the function of x. So what you could do now is integrate that function of x. So this is an example of what's called an iterated integral. The innermost integral is the one you do first. And this is the one we just did. So you integrate the inside first, you integrate out the y, and now you're just integrating the x. And then you just run this through as you would. So you'd have your 9x squared from x equals 0 to x equals 1. Excuse me, x equals 3. You toss in the 3, 9 times 9 is 81. Subtract off the 0, and there it is. Okay. So iterated integrals, you work from the inside out. And once you integrate out a variable, that variable will never return. Right? That's just that's how we do the notation. So let's see what happens if we go the other way. So if I think about what's happening in this integral here, I'm integrating the y from -1 to 2. And then I'm integrating the x from 0 to 3. So I'm integrating over this rectangle. You follow? -1 to 2, 0 to 3. That's given us this rectangle here that we're integrating over. What if I switch things around, and instead of integrating y from -1 to 2 first, I'll integrate the x from 0 to 3 first, and then I'll turn around and integrate the y from -1 to 2. So let's see what happens. So -1 to 2, 0 to 3, 6xy squared dx dy. Now if you see one of these things out in the wild, once again, the first thing you want to remember is that we're always working from the inside out. So we would do the innermost integral first. And the innermost integral, we're integrating with respect to x. So that means we're treating y as a constant. So if I wanted to, I could factor the 6 and the y squared out. If I wanted to do this, I could even write it like this first. Help kind of punctuate that point. I'll integrate this x squared over 2 from x equals 0 to x equals 3 dy. You plug in the x equals 3, you get 9/2. Subtract off what you get when you plug in x equals 0, which is 0. So you get -1 to 2, 6y times 9/2 dy. And now you've got yourself an integral in terms of just y. So now you're back to Calc 1 or AP Calc. You can multiply the 6/2 and the 9. Excuse me. Yeah. So 3 times 27. So you take that 27 out front. That'd be 27 times y squared over 2. Y equals 2. Y equals -1 to 2. You toss in there, you got 2 squared, 4/2 minus -1/2. So what did I miss here? Am I doing the right? Is it 6xy squared? Yeah, 6xy squared, 0 to 3. We should get the same answer. Oh, it's y squared. That's why. That should be a squared there. Excuse me. Put the y squared in there. There we go. It helps if you copy the problem right. Okay, that would be 8 cubes over that. So there we go. Now we get our 9 cubes, which is 3, and we get the same thing, 81. Now we had a theorem back in chapter 15 that said the order of the partial derivatives didn't matter as long as the partial derivatives were continuous. That was Fubini's theorem. And I mentioned at the time there's a couple different ways to go about showing you why this is true. Well, we can show this is true I think more easily using integrals. That's Fubini's theorem. So if we think about why this is true for integrals, let's think about if I'm integrating with the order dy dx. So if I look at the inside, right, if I'm doing dy dx, the first thing when I'm integrating is I'm going to be looking from the inside out. So I'm going to start inside here. I'm going to be integrating that y piece, treating x as a constant. So I think of treating x as a constant, I'd have some fixed x value here between a and b. And if I fix the x, I'm slicing my surface here. So here's my z equals f of xy. I'd be slicing my surface and I'd be getting a curve. And by integrating this y, I'd be figuring I'd get the area under that slice. You follow? And then when I come through and integrate from a to b on the x, I'm basically taking the area of this slice and then I'm filling out the volume, thinking of it as an accumulation of those slices. So do you remember back when you did things like volume by cross-sectional area? I think the most famous part of that was like, remember the disk method? You had a volume of revolution and you chopped it up. You had a bunch of circles and you stacked them together to find the volume. This is the exact same thing that's happening, but it's happening in a general context. So this integral dy dx, you're going to fix an x You're going to get the height as a function of y at that particular slice. Integrate that. So that innermost integral is computing the area of one of these slices, and then the x comes in to sweep and fill it up from the back to the front. And that would fill out the volume you're looking at. If I reverse the order of the integration and now integrate the x part first, once again over a to b, we're treating y as a constant. So we'd be fixing the y value, slicing the surface in that direction would get us this curve. And as I integrate from a to b, we'd be finding the area of that slice. And once that's done, you integrate over y, and that fills it out from left to right. And so you get the same volume either way. So when you interpret these integrals as volumes this way, I think you see why Fubini's theorem works. It's just two different ways of taking that volume and slicing it up. Am I slicing it up, calculating area and putting it together one way, or slicing it up, finding the area, putting it together in the other way? Right? It's the same volume because it's the same solid. You're just slicing it up in two different ways. And you can use this result to prove that the mixed partials are the same, which we'll get to we'll probably get to that tomorrow. Well, actually, we should have time to do that tomorrow. Okay, find the volume beneath the surface z equals x over y, above the region described x from 0 to 1, y from 1 to e. So that's the big thing now, is that if our f of xy is bigger than or equal to 0 on some region r, the volume between the graph z equals f of xy and the xy plane is given by volume is double integral over the region R of f of xy dA. So we think of this here, we can think of this as the base of the solid. We can think of this as the height of the solid. And this is the area of the base. Right? So we're adding up height times area of the base. That gives us a volume. So that's the one dimension up of finding area as the integral f of x dx. So in this chapter, there's not much to do here. There is a little wrinkle we'll talk about here in a minute. But there's not a lot to do here. Typically, my advice when given a volume problem is to first either sketch the solid or sketch the region. Here they tell us what the region is. It's a nice friendly rectangle. X is going from 0 to 1. Y is going from 1 to e. So there's our rectangle there. So if I want the volume, that's a double integral over r of the height dA. And we actually have a couple different options for dA now. We can chop up the x's or we could chop up the y's. So if I want to do, let's see, my f of xy is x over y. So we could do dx dy, or we could do dy dx. If I look at the order dx dy, I'd be fixing a y value and then seeing what the x runs between. So I'd be fixing some y value, and I'd be looking at what the x runs between here. The x runs between 0 and 1. And then the y would run from 1 to e. If I turn my head sideways and look at what's going on, I would be fixing the y fixing an x and seeing what the y would run between. So if I fixed an x, the y would still go from 1 to e because it's a rectangle. And then the x would come in and sweep from 0 to 1 to fill out that rectangle. Right. Are there any questions on setting up the integral there? It'll get more complicated in the next section, but that's kind of the thought process you want to get into. The innermost integral means you're fixing the outermost variable. So in the first integral, we're fixing y, looking what the x runs between, and then what the y runs between to fill out the region R, and then vice versa for the second one. Now in this particular case, it doesn't really matter which one we do first. We can kind of actually split this up. So if we started off with like the first one, say, we're integrating with respect to x. We can treat y as a constant, so we can move the constant out front. And then we could actually integrate this here. Same way you would like in Calc 1. 1/2 x squared, x equals 0 to x equals 1, dy. So that would get you 1/2, which you can bring out front. And you integrate that. That gets you your natural log. In this particular case, everything in sight's positive, so we don't need the absolute values there. Whoops. You got the natural log of e, natural log of 1. Natural log of e is 1. Natural log of 1 is what? 0. Yeah. So there's your 1/2. And it was interpreted as a volume, so that would be like cubic units or whatever. Okay. Cubic units. And you can, I'll leave it to you. I think, yeah, so you can do it the other way and show that you also get 1/2. All right, now something else that you can do with this, and you'll see this, like, what was the major, was it physical chemistry books do this all the time. So let's take a look at this integral again. So when you can factor your integrand here as a function of x and a function of y, we did this. We went ahead and did this. Then they'll say, well, wait a minute. This thing in here has nothing to do with the y's. There's no y's in the integrand. There's no y's in the limit of the integral. So this is a constant as far as the outermost integral is concerned. And so you'll often see this happen. Is you'll often see double integrals written as a product of integrals. And you can only do that as long as your integrand factors, function of x, function of y, and the limits on the integral are constants. Then you can get away with this kind of thing. This happens in physical chemistry all the time because you're integrating off to infinities and stuff. And anyway, so if you see this kind of maneuver, that's what's going on. All right, they're using the same principles, and we'll have occasion to take advantage of this kind of thing later on. I just want to show that to you now. I'll leave this one for you to do. Integrate given the order and then check your answer by switching the order of integration. All right, because we only have like a couple minutes left. So this, consider that your homework problem for tonight. So tomorrow we'll pick up with this and sort of talk about why you would pick one order of integration over another. So we'll work through example 5. We'll talk about the average value, which will be a callback once again to Calc 1. And then we'll talk about this problem. This problem is going to be on your take-home this week. I'm going to have you work through this problem. And then we should have time to use Fubini's theorem for integrals to prove Fubini's theorem of mixed partials. Okay. Then we'll start moving into more general areas that aren't rectangles. And that's where things can get a little more complicated. All right, so as always, folks, I appreciate you tuning in. It looks like it's going to warm up. It was in the 30s this morning. But it looks like it's going to be a pretty nice day the next couple of days. So I hope you get outside and enjoy the fall colors. And we'll see you tomorrow.